Good morning, everybody. I am Dr. Lennon, Associate Professor from VIT University, Chennai campus. So today we are going to see about electrical machine analysis using finite element method. So the type of motor we are going to analyze today is switched reluctance motor. The window shows a 5 HP switched reluctance machine specifications like outer diameter, bore diameter, shaft diameter, required rated current, rated voltage, rated speed, output power, required torque, everything. So based on these specifications, so we need to design a machine in a finite element platform and verify the required torque, speed, everything is obtained by means of this specification. So open the Motorsolve installed in your computer, which is a finite element analysis software from Infolitica Corporation. So as far as Motorsolve is concerned, at present in original version we have 5 different types of motor you can analyze: switched reluctance machine, induction machine, permanent magnet machine, synchronous machine, brushless DC, synchronous reluctance, and DC motor. Now we are going to design a 5 HP switched reluctance machine. So in this video I explain a step-by-step procedure how you model a switched reluctance machine in Motorsolve software. Once if you open our software, so create a new document. Click create a new document. In that we have 3 different types of motors available in trial edition, and in original edition it is 5. So we are going to design a switched reluctance machine. So choose a switched reluctance machine and click OK. The next one is, it comes general settings. So you have commands. So whereas you need to save, help, whatever the thing you want, you can do it in command option. Design, you need to have a design specifications in settings, general settings, rotor, stator windings, materials, everything you need to provide it in design settings. And in result you can obtain different performance characteristics, both static analysis as well as transient analysis. So in static analysis you get a different flux linkage curve, inductance curve, static torque curve, torque versus speed, static analysis, motion analysis, and in field analysis you get instantaneous field line probe, or probe, everything. So different performance view is possible in this case. And materials, if you want to change materials, you can change materials. Material library is also included in this software. So let us start with the design. So we are going to design a 5 HP machine, as I already told you. So with this specification, so the initial thing is supply voltage. The rated supply voltage is 440 volt AC. Rated current is 12 amps. Rated speed is 1500 RPM. The outer diameter is 147 mm. So if this window appears, you just click always perform dimension scaling and click OK. So the air gap we have is 0.5 mm. Stack length is 200 mm. So you have 2 options: rotor, interior as well as exterior. So if you have interior rotor, so this is a usual case. If you want to design a hub motor or outer rotating rotor, you can choose exterior rotor also. That is also possible. If you choose exterior, automatically see the rotor will come on the exterior side and your rotor is on the interior side. But as far as our specification is concerned, we are only designing a inner rotating rotor. So inner rotating rotor, and rotor type, it's general. So if you want to import from any DXF file, any CAD model, you can import that different rotor also. Number of rotor poles, so it's a 4-phase machine, so number of phases is 4. Obviously the number of stator poles is 8 and the number of rotor poles is 6, a default one. Suppose if you want to change the number of stator and rotor poles, you can choose from the drop-out box, or otherwise if you click manual, you can place any number of stator poles and rotor poles. So friction loss, I calculate friction loss based on 0.5% of the rated power. So it will be approximately 19 watts. So windage loss is also 0.5% of the rated power. Shear load losses is also 0.5% of the rated power. So approximately it is 19 watts per a 5 HP machine. So once if I give just general settings or get over. If you want to save the file, you can save the file at any instant. Save the file. So just I save the file in the desktop called name that as switch reluctance machine 5 HP. Save. So the next one we are going to see is a rotor. You click rotor, automatically it will comes for rotor dimension. You just go for protected dimension, drop it out, check whether any protected dimensions are marked. Suppose if it marked like this, simply you unmark the thing and go for each and everything you need to check with. So here the first thing I started with shaft diameter, because that diameter, that specification is available with me. So the inner diameter is 28 mm, so I specified 28 mm, and the bore diameter also available with me, so that is 98 mm. So based on that, if you see here, automatically the core thickness get varied. So no need to worry about calculate separately core thickness. The second one we need is pole depth, that is pole height. So the pole height we required is as far as this one is specification is concerned, stator pole height is 29.2 mm. So 29.2 mm, 29.2 mm. So you get a pole height of the 29.2 mm. So pole width, so pole base is also the same thing, so that it is easy to merge. So because the pole depth is 29.2 mm both sides, so it is divided by 2, so it will come 14.6. So this will be approximately 14. This is also make that as 14, and rotor pole angle is 23. This is also pole width, it is 14.6, so that you have a square shaped value. So this will be the thing. So your inner diameter is 28 mm and outer diameter is 98 mm. So this makes your rotor specification modeled in the Motorsolve. And if you want to change this pole base as well as pole tip radius, you can change that also. Save the model. Then once if you finish rotor modeling, go for stator. So in this we have two portions, one is coil and another one is about stator. So in the stator, you know the outer diameter already specified 147, inner diameter is already specified, back end thickness is also specified. Suppose if you want to increase the slot area and slot depth, so you can increase the slot depth or slot area like this. See, the pole angle is automatically get increased. so the pole height get increased. And tooth angle, if you want to vary, you can vary tooth cap angle, tooth cap width. So width, no need to have this much to so you can reduce that one. Tooth width base, base is so with tip everything is there. So tooth cap angle is 22 mm, tooth gap width is 18, and tooth width base is 20, and this is also 20 mm. Stator pole angle is 23 mm. And back end, and here it comes for coil angle. Suppose if you want for 90 degree, you can have a 90 degree coil angle so that the windings get straightened. So coil insert, you can give some space, so I just give 1 mm space to wound to give the space. So coil length 14 mm, it is there. Coil separation, and a coil with base, coil with tip. So you can separate your if you want to reduce the space of the coil, you can reduce the space of the coil also. So, and a few things we need to have in the rotor is pole width, it is 22 mm. Old it's 15. This one is pole width is 22, and this is 22. So the rotor pole angle is slightly more than that is the rotor pole angle is 26 degree approximately, and stator pole angle is to see the stator pole angle, it is approximately 20. Stator pole angle is 23 mm. So always in switched reluctance machine, if you design rotor pole angle little bit greater than your stator pole angle, your torque ripple as well as the average torque is better when compared with both the pole angles are same, or otherwise the stator pole angle is greater than the rotor pole angle. So for that purpose only we kept this rotor pole angle a little bit greater than the stator pole angle. So that's all about modeling of rotor, stator, and if you check with the general settings, everything is there. If you want to see it in a 3D manner, you can rotate your machine and you can see the stack length is 200 mm. So you have 8 stator poles, 6 rotor poles. So each diagrammatically opposite poles constitute a phase. So this is a 4-phase machine. So we model a winding also, and a winding gap also we can specify. See the 1 mm gap with the pole. So and the air gap is also specified. It's a 0.5 mm thickness. See the air gap. So air gap, it is clearly seen between stator and rotor. So the, for example, if this is the first phase is aligned, whereas the third phase is exactly unaligned, which shows the design is the design constraints matches with the model structure. The next thing is here we model the windings. The next thing is we go for a stator winding, and you need to specify number of turns you are going to use per phase. So the number of turns per phase we are going to use is 172, so which is shown in the specification itself. For 172 number of turns per phase is 172. So I specify the same thing here. And the fill factor, usually we have a slot fill factor of at least 40% to have a better performance of the machine. So 172 stator windings, and the stator end windings, if you see the stator end winding, you can specify the gap of the end winding also. Now it is 1.63. Suppose if you want to reduce, you can reduce to 1, so that the end winding gap will get reduced, but it makes more heat towards the stator core. So usually we maintain 2 mm gap between this winding, end winding, and the stator core. So this will come to end for modeling of the machine. If you want to animate the windings, phase windings, you just click on animation on. So automatically you can see the direction of the current in each and every phase. So it's a 4-phase machine: 1 A phase, B phase, C phase and D phase. So how the current will get conducted in the coil is automatically understandable. So you just switch off the animation and you need to trace the results now. So what you have to do is, see in this one, what is the advantage of Motorsolve is, once if you specify number of turns and the area of the winding, automatically it will calculate end winding resistance, end winding inductance, winding phase resistance, and this one is the optional one which you are going to provide, and conductor area also. So based on this you can easily find out which coil, which copper wire you are going to use for your model. The next one is post-processing. Before that we need to solve the model. Post-processing, before the post-processing we need to solve the model, and you can solve the model based on your requirement. So first thing, just I want to see the flux linkage of the machine. So for the percentage of the rated current, so that means 12 amps current, number of current intervals you can specify anything. Suppose if you want only 2 current intervals, you just specify 2 current intervals, or otherwise if it is more than 3 that would be better. So I just specify 10 current intervals. Number of rotor positions is 15. Analysis method, you have 2 analysis method. One is semi-analytic and complete FEA based. Choose complete FEA based, and speed and accuracy you can choose according to your wish. One is fastest and 1 is most accurate, but it takes more time. First one is fastest, but a little bit less with less accuracy. Let us start with the fastest one and check with the most accurate one afterwards. Just I want a flux linkage, click the flux linkage and view result. So wait for some time, see here. So the machine is going to solve the model. It takes some time. See, it takes a minimum of 56 because it's a complete finite element analysis. Minimum it takes 56 iterations, so that the solution we get is somewhat near to the predicted values. So then rotor positions and all, if you want to change, you can change the rotor positions and all according to your requirement. So this is one of the most powerful software tool available for instant analysis of electrical machines. So no need to spend much time in this software to predict the basic performance of the machine. So whereas optimization and all, we need to go for magnet software, whereas for basic performance prediction, Motorsolve is a best tool. Now we solve the flux linkages for different currents for the 0 to 110 amperes. So you see here, so you get a different flux linkage for the maximum current to minimum current, that is 0 current. Here this point is called as aligned flux linkage, and this point is called as unaligned flux linkage as far as switched reluctance machine theory is concerned. So this is the flux linkage. This is for complete FEA, and you can use the semi-analytic method also, which is quite faster to get the result. Once if you analyze the results of semi-analytic, so it is quite easy to get the result more quickly when compared with the previous method. But finite element analysis is always good for industrial point of view. For academic side, you can use the semi-analytic method as well as finite element method. Yes. So now this is a semi-analytic analysis for flux linkage. See, the same value is obtained, but with smooth curvature, but a little different, little error we can get in this one. So similarly, you can see the inductance value. The same thing, you can change either semi-analytical value or otherwise finite element based analytical, so as your wish. So click the inductance and click the view result. So it will take some iterations to calculate the inductance value of the machine. So 13 iterations we need to wait. So for the rated for the current of 0 to 10 amperes. So likewise you can solve the model for each and every performance requirement. See, so this is the inductance value for different currents, 2, 4, 6, 8 and 10 amps. See here, 2 amps, 4 amps, 6 amps, 8 amps and 10 amps. So it's somewhat similar, the inductance value. So similarly you can do the analysis, view the results for static torque. See, the static torque for this is for the 10 amps current, and this is for the 8 amps current, this is for 6 amps current, and the green one is for 4 amps current, 2 amps current, and this is 0 current. So these are the different torque values, and similarly you can find the finite element value of a torque also. Say it takes some time. Yes, so this is the finite element value for different rotor positions. So this one is not good because it only provides for only 0, 45 degree, 90 degree, like that. So the rotor angle, for this particular rotor angle only it provides the result, so it is not smooth. So likewise you can specify the torque speed analysis chart for static, and you can select the result quantities, whatever the result quantities you want for static analysis. So for example, if you want a current and if you want x-axis as current and as a quantities current, so you just view the result. So it will provide a torque versus current value. See, for different values of current, what is the torque. So similarly for different values of current, if you want to know the energy and co-energy, so that also you can visualize this one. See, so different field energy values for different current for different rotor positions. So likewise co-energy value. So for different rotor angles, this is the co-energy value for different currents, and you can view the instantaneous fields also. See, the instantaneous fields you can view. So the maximum flux density available at this point is maximum. So this one, the maximum flux density available here is point at this point is 0.39. So which is given here 0.392. So here it is 0.83, so it is yes, it's a 0.83, so at the tip. So here whereas in this one it is 0.01 somewhere in here, so it's very less. So this is the excitation current, the current present, maximum current present in the machine. So the flux density is 0.392. So for motion analysis, choose the motion analysis, and whatever the result quantities you required, you can choose. For example, if I want output power, choose the output power, and with respect to torque, choose that one. Choose the motion analysis and view result. So it will take more time because the iterations for motion analysis minimum it is extended for 15 to 20 minutes. So it takes 386 iterations, so we need to wait for that one. After that we can predict the output power with respect to the torque. So if you want to stop and if you want to see the results in mid, you can press the escape button and you can view the result. So as it takes more times, so I just want to press the escape button just to stop the operation. So once if you have finished the 386 iterations, so automatically you can get the results of output power versus torque. Not only output power, you can view the other parameters like torque, input power, voltage, current, flux linkage, losses, energy and field energy and co-energy with respect to any x-axis quantity. So from this you can calculate the efficiency, power factor, other things you require. Suppose if you want to export the results, whatever the results you obtained either in static analysis or otherwise in transient analysis, so you have an export option. So let us explain that thing. Once if you get the flux linkage curve, suppose if you get this curve, if you want to have this if you want to view the data, you just click view data. Automatically there are data with respect to different currents for different rotor angle. Automatically it will show it in a tabular manner. If you want to export, you just click export. Automatically it is going to save in Excel file. You can save it in any name, for example flux linkage. So you can save it in desktop, save, close. So you can have this one here in the desktop. Flux linkage is there. So if you open this, you can get the flux linkage curve with respect to different rotor angle for different current. So you can plot the curve as you wish in the Excel sheet like this. So this is one of the biggest advantage in Motorsolve platform. So that's all about the modeling of 5 horsepower switched reluctance machine in Motorsolve platform. Thanks for watching.